Welcome to Apache Beam's Advanced Concepts, Part 4 in my Dataflow video series. This covers non-optional material for Google's Professional Data Engineering Certification exam, which means we will be covering testable material. Google may even ask 3 or 4 questions on Beam's advanced concepts, so they're actually really important to learn. So if you're ready, let's get started. We are covering 3 advanced topics, which include windowing, watermarks, and triggers. In any data processing system, there is a certain amount of lag between the time a data event occurs, known as the event time, which is determined by the timestamp on the data element itself, and the time the actual data element gets processed at any stage in your pipeline is the processing time, which is determined by the clock on the system processing the element. In addition, there are no guarantees that the data events will appear in your pipeline in the same order that they were generated. Let's look at the advanced concept of windowing. Windowing subdivides a P collection according to the timestamps of its individual elements, transforms that aggregate multiple elements, such as group by key and combine, work implicitly on a per window basis. They process each P collection as a succession of multiple finite windows though the entire P collection may be of unbounded size. Windowing is particularly useful for unbounded P collections or streaming events. The window function is assigned to a P collection. It allows you to subdivide the elements of a P collection according to their timestamps. The whole point of windowing is to enable grouping or aggregation operations over unbounded collections by grouping elements into finite windows. This makes it easier for them to process. The unbounded P collection can be processed as a session of finite windows. Think of it as a way of processing streaming data by processing it in small little groups. All right, let's look at windowing a little bit more. So here in this example, as you can see to the right, if you follow along with the graphical representation, we're actually creating an unbounded P collection by reading a set of key value pairs using the Kafka IO. Now, it is interesting to note that window grouping occurs on an as-needed basis. If you set a windowing function using the window transform, each element is assigned to a window, but the windows are not considered until group by key or combine aggregates across a window and key. So next we're going to apply a Pardue to the collection and then later group the results of that Pardue using group by key. The windowing function has no effect on the Pardue transform because the windows are not actually used until they're needed by the group by key, as we said earlier. The subsequent transforms, however, are applied to the result of the group by key, and data is grouped by both key and window. All the elements are by default part of a single global window. All right, here we have 2 examples of a pipeline that reads from a batch file, applies aggregations using group by key, and then applies the Pardue transform. Now, the key difference here is the top pipeline does not have windowing, and the bottom one does. So how would we go about that in comparison to one another? So on the above pipeline, we create a bounded P collection by reading lines from a file using the text IO, which is an Apache Beam class that must be imported to use. Now this is very useful for reading a P collection from one or more files, and we're going to get into that a little bit later. The IOs have their own video. They're pretty important. We then group the collection using group by key and apply a Pardue transform to the grouped P collection. In this example, the group by key creates a collection of unique keys, and then Pardue gets applied exactly once per key. So windowing is not used, but in the bottom one, it is. So in the bottom one, as before, the pipeline creates a bounded P collection by reading lines from a file. We then set a windowing function for that P collection. The group by key transform groups the elements of the P collection by both key and window based on the windowing function. The subsequent Pardue transform gets applied multiple times per key and once for each window. Now you can define different kinds of windows to divide the elements of your P collection. Beam provides several windowing functions, which include the fixed time windows, the sliding time windows, the per session windows, and finally the single global window. Now, if you remember, that's already set by default. So that's the default one. Let's look at the fixed time windows first because it is the simplest type. Now, this one represents a constant non-overlapping time interval for a constant duration, let's say a minute. Since it's non-overlapping, this means that each element is assigned its own window. So, for example, let's consider windows with a 30-second duration. All the elements in your unbounded P collection with the timestamp values of 0 up to but not including 30 seconds belong to the first window. Elements with the timestamp values of 30 seconds up to but not including a minute belong to the second window, and so on. Here's the example code for fixed time windows. Notice how we've imported window from Apache Beam. We've defined our output P collection fixed windowed items. Our input P collection we've named items. The transform we're using is the window, and we're calling beam.windowInto, to which we pass the argument window.fixedWindows and passing in our time in seconds, which in this example is 60. Sliding time windows allow for overlapping and are particularly useful for taking running averages of data. For example, you could have 1-minute windows every 10 seconds. Because it allows for overlapping, a single element could be assigned to more than one window. In Dataflow, overlapping windows are called hopping windows. Just be aware that they are the same thing. Here we have an example of what the code looks like for sliding time windows. We've imported window from Apache Beam, and we've set the window to be 30 seconds every 5 seconds. Here we have an example of a sliding time or hopping windows question for the exam. Your cryptocurrency trading company visualizes prices to help your customers make trading decisions. Because different trades happen in real time, the price data is fed to a data pipeline that uses Dataflow for processing. You want to compute moving averages. What should you do? Well, we just talked about that in the last slide, that sliding or hopping windows is what you would use to compute running averages. So that's the answer. Okay, the next window type that we have is called session windows, and that is a different session window is created in a stream when there is an interruption in the flow of events, which exceeds a certain time period. Now you're going to apply this on a per key basis, and this is particularly useful for a regularly distributed data with a respect to time. And over here on the right, we have a breakdown of what that would look like. The following example code shows how to apply window to divide a P collection into session windows, where each session must be separated by a time gap of at least 10 minutes. Note that the sessions are per key. Each key in the collection will have its own session groupings depending on the data distribution. All right, let's look at an example of a session windows question. Your online shopping company needs to know when a user has not interacted with the site in 30 minutes. So right here, right off the bat, we know that there's an event, there's a trigger, and it happens to be 30 minutes. That's our gap time. They need the website to alert the user once they have been idle for too long. You use Cloud Dataflow to process the interaction events and decide if an alert should be sent. How should you design the pipeline? Well, here our answer is implement a session window with a gap time duration of 30 minutes. All of that is held within the question itself. All right, this one's really short and sweet, so I just put it all on the same page here. So by default, all data in a P collection is assigned to a single global window. If you do not change your window on a P collection, a single global window will apply. So if you want that to change, you actually have to go in and change the settings. But over here on the left here is the example code for that. for the single global window. Just, you really do need to know that that is the default. All right, let's talk about watermarks and late data. The odds of you having a test question on this particular subject is pretty high. So this is stuff you actually really do need to know. So Beam tracks a watermark. It is the system's notion of when all the data of a certain window can be expected to have arrived. Once the watermark moves past the end of a window, any further data elements that arrive with a timestamp within that window are considered late, and you can determine how late data is treated. Now, when do you want to use a watermark? You want to use it to seek feedback, reflect on performance, explore new techniques, set personal goals, or to iterate and adapt. Okay, let's look at an example of a watermark question. In a data flow processing pipeline, which concept describes timestamps attached to incoming messages? Well, we just learned about that, and we know that that is a watermark. So how can we manage late data? You can allow late data by invoking the .with allowed lateness operation when you set your P collections window strategy. The following code example demonstrates a windowing strategy that will allow late data up to 2 days after the end of a window. Now, this is just all information that's useful to know. An unbounded source provides a timestamp for each element. Depending on your unbounded source, you may need to configure how the timestamp is extracted from the raw data stream. However, bounded sources, such as a file from text.io, do not provide timestamps. If you need timestamps, you must add them to your P collection elements. You can assign new timestamps to the elements of the P collection by applying a Pardue transform that outputs new elements with the timestamps that you set. Now over here on the right is the example code on how to apply a timestamp. All right, let's look at an example timestamp question. You have hundreds of IoT devices that generate 1 terabyte of streaming data per day. Due to latency, messages will often be delayed compared to when they were generated. You must be able to account for data arriving late within your processing pipeline. What should you do? Okay, so what you should do here is you want to enable your IoT devices to generate a timestamp when sending messages. You're going to use Dataflow to process the messages and use windows, watermarks with timestamps, and triggers to process the late data. So what exactly are triggers? When collecting and grouping data into windows, Beam uses triggers to determine when to emit the aggregated results of each window. If you use Beam's default windowing configuration and default trigger, Beam outputs the aggregated result when it estimates all data has arrived and discards all subsequent data for that window. You can set triggers for your P collections to change this default behavior. Beam provides a number of pre-built triggers that you can set. Event time triggers. These triggers operate on the event time, as indicated by the timestamp on each data element. Beam's default trigger is event time based. Processing time triggers. These triggers operate on the processing time, the time when the data element is processed at any given stage in the pipeline. Data-driven triggers. These triggers operate by examining the data as it arrives in each window and firing when that data meets a certain property. Currently, data-driven triggers only support firing after a certain number of data elements, composite triggers. These triggers combine multiple triggers in various ways. All right, let's look at an example of a trigger question. Which of the following is not one of the 3 main types of triggers that Dataflow supports? Trigger based on element size in bytes, trigger that is a combination of other triggers, trigger based on element count, or trigger based on time. Well, we know that there's one on time, and we know that there's one that's a combination, and the one that's on count, yeah. Based on size in bytes, nope, that's definitely not one of them. That's going to wrap up this lesson on advanced Beam concepts. I'll see you in the next lesson, which is going to be on sources and syncs.